Okay, so in our last video of chapter 19, we're going to talk about ways to make amines. So there's a recurring theme when we talk about the ways to make amines. And those two themes are, one, pretty much any functional group that has a nitrogen can be reduced to produce an amine. So in our summary near the bottom here, we have azide to amine, nitrile to amine, nitro group to amine, amide to amine, and imine to amine. So all of those nitrogen containing functional groups can be reduced to produce an amine. So for some of them, we also have how you make that nitrogen containing functional group. So we'll talk about those when we get to those relevant sections in the chapter. The next other important aspect that most of those have is the theme that we start off with some functional group that contains nitrogen, and then we do some chemistry where we add on an additional alkyl substituent. So in this particular case, for example, if we start off with ammonia, 0 alkyl substituents to nitrogen, and do one of these processes, we then end up with a primary amine. If we start off with a primary amine, do our chemistry, we end up with a secondary amine, again adding one more R group. Or if we start off with a secondary amine, do this process, we end up with a tertiary amine. So those are really our two main recurring themes. Make something that contains a nitrogen and reduce it, you end up with an amine, and we're always adding one R group to the existing nitrogen. So for example, this method that we're calling reductive amination, we're going to convert an amine as our starter material, react that to produce an imine, which we already talked about not only in the previous chapter but also earlier in this chapter, condensation chemistry. So amine plus aldehyde or ketone gives an imine. Reduce the imine, you get a new amine. And notice the relationship, primary amine going to secondary amine. So we've added a new R group. So this appears in our summary here. So imine to amine. These are the reagents that do that transformation. You might say, well, how do I make my imine? You make your imine using your amine and an aldehyde or ketone. So our logic is always start off with something with nitrogen, do our process, and we'll end up adding one more R group. So if you start off with a primary amine, go imine and reduce, you get a secondary amine. If you want to make a primary amine, that means that you need to start with a nitrogen that has 0 alkyl groups. So we actually use NH2OH for that. NH2OH has 0 R groups connected to nitrogen. Do our imine analog reaction. So this is forming an oxime, still a condensation. Then reduce, produce a primary amine. So 0 bonds to alkyl groups, 1 bond to alkyl group. So already talked about our secondary amine, tertiary amine. To make a tertiary amine, you just use a secondary amine and an aldehyde or ketone. Slight twist here is you have to use a different reducing agent, but the process and the logic is still the same. So that was, in our summary, pathway E, reductive way, so imine to amine. The next is the acylation and reduction. So amine and acid chloride gives you an amide, You know that from acylation up here. So this was amine, and acid chloride gives you amide. And then reduction of that amide is going to produce an amine. So these are the reagents for the reduction. And so notice that if we do that process, primary amine ultimately ends up with secondary amine. So we're adding one additional R group, and we made some other functional group that contains nitrogen, and that got reduced. Then next one is nitro compounds. So I already talked in the aromatic chapter of how you make nitro compound. The easiest way is to do the EAS, nitric acid, sulfuric acid, of an aromatic ring. Here we're seeing that a nitro group, the NO2 group, can be reduced to an NH2 group using a variety of different reducing agents. Hydrogen gas in a catalyst works, or a metal such as iron, zinc, or tin with HCl, that can also be used. So nitro aromatic to aniline. And remember that this aniline is then useful because you can do diazonium chemistry and then make a bunch of other aromatic substituted products. The direct alkylation of amines is generally not easily controlled and therefore not really a viable synthetic pathway. That then brings us, so we've done C, D, and E. That just then leaves us B and A. So both of these are related in that we're going to introduce our nitrogen as a nucleophile. So the azide ion, which is N3 minus, you get it in ionic salts, for example. This is sodium azide. That's a good nucleophile. So that N3 minus can be used as a nucleophile to displace some leaving group. So for example, this bromine. So this starter material reacting, for example, with sodium azide, the azide does a nucleophilic substitution, substitutes the bromine for this N3 group. Then the whole point of this is that functional groups with nitrogen can be reduced to an amine. You take your alkyl azide, reduce it using these reagents, and that converts the N3 to an NH2. So ultimately, we're going from an alkyl group connected to a leaving group, substituting that leaving group by an azide, and then converting that azide to an NH2. So this is an indirect nucleophilic substitution, getting your leaving group to be substituted in this two-step process by an NH2. A similar way, similar type of thing, is to use cyanide as your nucleophile. So our general strategy is the same. Starting material has a leaving group. That leaving group gets replaced by a nucleophilic substitution, producing now this nitrile. That nitrile has a nitrogen, so you reduce that and you end up with an amine. In this color-coded example, notice that we've now introduced an extra carbon and a nitrogen. So both the carbon and the nitrogen get reduced. So the overall atom change is we're going from an R group connected to a leaving group to an R group connected to a C and an N, ultimately after reduction to an R group connected to a CH2 and an NH2. So notice that this transformation is not substituting the leaving group for an NH2, it's substituting the leaving group for a CH2, NH2. So that's the main difference between the azide methodology and the cyanide methodology. Azide puts a CH2 where the leaving group, an NH2 where the leaving group was. The cyanide method puts a CH2, NH2 where the leaving group was. So that's important when you're thinking about number of carbons in your product compared to number of carbons in your starting material. So those are similar routes, but they are not interchangeable. One introduces NH2, the other introduces CH2, NH2. And then the last two reactions are kind of miscellaneous reactions. We have them summarized at the bottom. The Gabriel synthesis is a way to make primary amines. So you essentially take this, deprotonate, then, alkylate, and then liberate your amine. Then the second reaction is called a Hofmann rearrangement. And a Hofmann rearrangement converts an amide into an amine. But if we look at the number of carbons, you'll see that the relationship here is that there's one less carbon in our amine product than there was in our starting amide. Schematically, we've basically just chopped this CO out of that molecule. So this is why I call it a chain shortened amine as being the product, because we've shortened the carbon chain there by one carbon. So the mechanism is then provided there. So what we have now is the completion of our chapter 19 information. So notice that the synthesis of amines really involves the reaction of other amines and is normally followed by a reductive step.